thinking about the universe as a giant quantum computer. It's a pretty wild idea, right? Like, something out of a science fiction movie. But some smart people, physicists, and cosmologists actually talk about this. They wonder if the very fabric of reality, everything around us, isn't just behaving like a computer, but is a computer. A massive, complex quantum one. It's not a new thought, this idea of the universe as something computational. People have thought about the universe as a clockwork mechanism or a giant machine. But quantum computer adds a whole new layer to it. It makes us look at the smallest parts of everything, the weird rules they follow, and then try to see if that fits into the idea of processing information. Let's be honest, it's a big concept. It sounds kind of out there. But sometimes, to understand big things, you need big, maybe even strange ideas. This isn't about saying, yep, it's definitely a computer, case closed. It's more about using a powerful metaphor, a way of thinking, to try and get a handle on what reality actually is. So, what are we even talking about here? When we say computer, we usually think of our laptops or phones. They take input, they process it using bits, those zeros and ones, and they give us an output. A quantum computer does something similar, but its fundamental building blocks are different. They're called qubits. Imagine a light switch. It's either on 1 or off 0. That's like a classical bit. Simple. A qubit, though, is weirder. It can be on or off or both at the same time. It can be in a state called superposition. Think of it like a spinning coin. While it's spinning, it's not heads and it's not tails. It's both until it lands. Only when you measure it, does it decide to be heads or tails. And it gets stranger. Qubits can also be entangled. This means 2 or more qubits get linked up in a special way. No matter how far apart they are, if you change something about one, the other instantly changes too. It's like having 2 connected coins. You flip one, and before it even lands, you know what the other one will be. Einstein called this spooky action at a distance. It's a real thing, though. It's been tested. So a quantum computer uses these weird properties, superposition and entanglement, to do its work. It can process a lot more information at once than a classical computer. It can explore many possibilities simultaneously. That's why people are so excited about quantum computers for solving really tough problems that classical computers just can't touch. Now imagine the entire universe operating like that. Every tiny particle, every interaction, every bit of energy, maybe even space-time itself, behaving like a qubit or an entangled system. It's a lot to wrap your head around, but if you start to look at the universe this way, some things begin to click, or at least make a bit more sense as a possible explanation. One of the big reasons people even go down this road is because of information. What is information, really? We usually think of it as data on a hard drive or words in a book, but some physicists think information might be more fundamental than matter or energy. They think the universe isn't just made of stuff, but it is information structured in a certain way. Think about it. When an electron interacts with a photon, it changes state. It absorbs energy or emits it. It moves to a different orbit. That change in state, that interaction, can be seen as a processing of information. The electron state before the interaction is input. The interaction itself is the computation, and its state after is the output. And this happens constantly everywhere all the time across the entire universe. Trillions upon trillions of these tiny interactions all happening in parallel. And everything, truly everything, at the smallest scales is quantum. We're not just talking about some particles in a lab, we're talking about the very fabric of reality. Atoms, protons, electrons, quarks, they all play by quantum rules. They exist in superpositions, they get entangled. They don't have definite properties until they are measured. This isn't just a small part of the universe. This is how the universe works at its deepest level. So, if everything is quantum and if everything is constantly interacting and changing states, isn't that, in a sense, a form of computation? The universe is constantly evolving. From the Big Bang through star formation, galaxy clusters, the creation of elements, to life itself, it's a continuous process of transformation. And each transformation involves changes in the states of fundamental particles and fields. If you define computation broadly as the manipulation and transformation of information, then the universe itself seems to be doing a whole lot of that. There's also the mind-bending topic of black holes. Stephen Hawking and others showed that black holes aren't just cosmic vacuum cleaners. They actually emit radiation very slowly. This radiation is called Hawking radiation. But there was a big problem, something called the information paradox. When something falls into a black hole, does the information about it get completely destroyed? Quantum mechanics, the rules that govern the very small, says information can never be truly destroyed. It can be scrambled, but it always exists somewhere. If black holes destroy information, then quantum mechanics is wrong. If quantum mechanics is right, then the information must somehow escape even if it's totally unreadable. This paradox has led many to believe that information is a foundational part of the universe, that it's conserved just like energy. And if information is conserved and processed, then the universe starts to look even more like a system that handles information in a fundamental way. A giant information processor, a computer. Another point that sometimes comes up, though it's a bit more on the philosophical side, is the fine-tuning of the universe. The fundamental constants of physics, like the strength of gravity, the charge of an electron, the mass of a proton, seem to be precisely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe as we know it couldn't exist. Some people look at this and wonder if it's like a set of parameters or an algorithm that was very carefully chosen. Like the universe is running a program with specific initial conditions that allow for all this complexity to emerge. Okay, so if the universe is a quantum computer, how would it even work? What would be the qubits? What would be the processor? What's the program? The qubits of the universe could be anything at the most fundamental level. Maybe they're fundamental particles themselves, like electrons and photons, constantly in superposition and entangled with each other. Or maybe it's even smaller, down at the Planck scale, the smallest possible unit of length and time. Perhaps space-time itself, in tiny, tiny units, is granulated, and each tiny unit acts like a qubit. Some theories even suggest that space-time isn't smooth, but made of a network of interconnected nodes, like a vast quantum foam. And what about the processor? What does the computing? Well, that'll be the laws of physics themselves. Gravity, electromagnetism, the strong and weak nuclear forces, these aren't just rules that things follow. They are the mechanisms by which things interact, change state, and process information. Every time a particle decays, every time two atoms bond, every time light travels through space, it's an operation, a computation guided by these fundamental laws. The program, that's the big one. It could be the initial conditions of the Big Bang combined with those fundamental laws of physics. The universe started in a very specific low entropy state, and from that initial program, everything else unfolded. The entire history of the universe from that first moment until now can be seen as a continuous unfolding computation. Every interaction, every physical process is a step in this cosmic computation. A star forming, a galaxy rotating, a brain thinking, these are all incredibly complex, emergent phenomena, but they're built from the ground up by these fundamental quantum interactions. It's not like the universe runs a single program from beginning to end. It's more like it's constantly running billions upon billions of interwoven, parallel computations all at once. It's a massively parallel, distributed quantum computer. One of the really important concepts here is decoherence. If everything is quantum, if everything is in superposition, why do we experience a classical world? Why does an apple, when I look at it, not also exist as an orange or a banana until I observe it? Why does it just seem to be an apple? Decoherence is the process by which quantum superpositions collapse into definite states. It happens when a quantum system interacts with its environment. The environment measures the quantum system, forcing it to pick a definite state. In the context of the universe as a quantum computer, decoherence is constantly happening. Parts of the universe are constantly interacting with other parts, effectively measuring each other. These interactions cause quantum superpositions to collapse, leading to the classical world we perceive. The universe is, in a sense, constantly measuring itself, and that process of self-measurement is what creates our familiar everyday reality. It's like the computer is running its operations, and these operations inherently lead to a readout or a measurement that we as observers within the system perceive as a fixed reality. Of course, this whole idea faces some big challenges and counter-arguments. It's not a done deal, not by a long shot. One challenge is just defining computation. If any physical process, any change in state is considered a computation, then the idea becomes almost trivial. A rock rolling down a hill could be seen as computing its trajectory based on gravity. A leaf falling is computing its path through the air. If the definition is too broad, then saying the universe is a computer doesn't really tell us much new. We need a more specific, meaningful definition of what it means for the universe to compute, especially in a quantum sense. It must go beyond mere physical interaction. It needs to involve information processing that uses superposition and entanglement in a non-trivial way. Then there's the observer problem. In quantum mechanics, the act of observation is crucial. It's what collapses the superposition. If the universe is the computer and it's constantly computing itself, who is the observer? Is it just parts of the universe observing other parts, or is there something outside, a cosmic observer, making the measurements? This can quickly lead into philosophical or even theological territory, which many scientists try to avoid when doing physics. If we are just subroutines within this grand computation, then our own observation is just another internal computation. And what about a designer? If it's a computer, who built it, who wrote the code, the program of the laws of physics? This is a question that naturally arises, but it's one that the scientific framework struggles with. The goal of physics is to describe how the universe works, not necessarily why it exists or who created it. Saying the universe is a computer can sometimes sound like it implies a programmer, which can be seen as bringing in an unnecessary outside agent. However, one could argue that the program is inherent in the universe's fundamental structure and initial conditions, without needing an external designer. Another hurdle is practicality. We can't exactly build a universe-sized quantum computer to test this hypothesis. It's more of a conceptual framework, a way of thinking about reality than a directly testable scientific theory in the traditional sense. It's hard to falsify. How would we prove it's not a quantum computer? These kinds of ideas often remain on the edge of physics and philosophy, inspiring new ways of looking at old problems, but not always yielding concrete, testable predictions. And why quantum specifically? Why not just a classical computer? The quantum aspects, superposition, and entanglement are key. If the universe was just a classical computer, it would mean that every particle has a definite state at all times, even if we don't know it. But quantum mechanics tells us this isn't true. Particles don't have definite states until measured. So, if the universe is computing, it has to be using these quantum properties. That's where its power and its difference from a classical view lie. It's the ability to explore countless possibilities simultaneously, to hold many realities in flux, until an interaction or measurement forces a choice. So, what are the implications if this idea turns out to hold some truth? What if the universe really is a giant quantum computer? First, it changes our understanding of our own place in the universe. If we're all just patterns of information, complex algorithms running on this cosmic machine, what does that mean for free will, for consciousness? Are we just incredibly intricate superroutines? It sounds cold and reductionist, but it also gives a profound sense of interconnectedness. Every thought, every feeling, every action would be part of the universe's ongoing computation. It also connects to the simulation hypothesis, which is related but not quite the same. The simulation hypothesis suggests that our universe might be a computer simulation running on another, more fundamental computer. If the universe is a quantum computer, it could simply be the fundamental reality, not a simulation within another one. It could be the prime computation, but the ideas often overlap because both suggest information is primary. This way of thinking also deeply affects how we understand reality itself. Time, space, matter, energy, they might not be the fundamental things we thought they were. They might be emergent properties of this underlying quantum computation. Perhaps time isn't a continuous flow, but a sequence of computational steps. Perhaps space isn't an empty void, but a network of interconnected qubits. It could also lead to new avenues in physics. If we think of the universe as a quantum computer, it might give us new tools or new perspectives to tackle some of the biggest unsolved problems. Could it help us unify quantum mechanics and gravity? Could it shed light on the nature of dark matter and dark energy, which make up most of the universe but remain mysterious? If these are just bugs, or features of the cosmic code, maybe understanding the code itself will reveal their purpose. Ultimately, this idea of the universe as a giant quantum computer is a thought experiment, a powerful metaphor, and an evolving scientific concept. It pushes the boundaries of what we think we know about reality. It makes us question our most basic assumptions. It's not something we can definitively prove or disprove right now, but that's okay. Science often starts with big, bold ideas that seem crazy at first. It's how we make progress. It's a way of asking deeper questions, of looking at the universe from a different angle. It makes us wonder if everything we see, everything we experience, is just the output of an unimaginably vast and complex quantum computation humming along since the very beginning, creating the cosmos, creating us. It leaves us with a sense of wonder, a feeling that there's so much more to understand about the fundamental nature of existence. And that's a pretty good place to be.